Okay, good evening, everyone. So before I start, any questions or issues? Okay, so um, um, last time at the end of the Wednesday lecture, we had started looking at different types of finite state machines. So if you recall, in the last lecture, we had kind of talked about how the hardware view of sequential systems corresponds to a graph where the states, the different state vectors which are possible, so different bit patterns that reside in the state vector, they kind of correspond to the nodes in a graph. And then every clock tick, when we update the state in the state register, that corresponds to moving between those nodes in the graph. So if you recall, kind of we had talked about representing a sequential system in terms of finite state machine that's shown out here. Um, and then the other thing we had looked at was that how there are sort of, we can think of finite state machine in broadly three categories. There was the acceptor category, classifier, and transducer. I had not covered the transducer. So acceptor state machines, basically what they do is they take a sequence of bits, or sequence of input symbols, and at some point they say, okay, is it an acceptable sequence or not? So we typically end up using it for things like looking for a pattern. So whenever a pattern hit occurs, then we say, aha, the input has that pattern or not. So this particular state machine was an example where we kind of the scenario was that the input was receiving characters, and at some point the input would be terminated by a special character, which was a dollar character. And kind of the idea is that if at any time through the dollar character appearing, if the substring UCLA was observed, then the machine would end up in this state called success, and it will kind of just stay there. So there is a self loop out here. And if we observe the dollar sign without having encountered an UCLA substring, then we would go to the failed state and stay there. So as long as characters are coming and we have not seen UCLA and the dollar sign has not occurred, we'll kind of keep hovering between the four states that you see out here: start U, found C, and found L. But if any of the conditions happen, namely either a dollar symbol occurs or we observe UCLA, then the former case we move to the failed state, which is the one at the top that my cursor is, and otherwise we move to the success state. And these are kind of the end states. We just stay out there. So, the success state is called accepting state, and the failing state is called as a rejecting state. So, in a sense, you can say that I can think of a set of all possible strings that end with dollar symbol, and we basically are saying that is the input uh, in the set where those strings consist of UCLA. So essentially, imagine a set of all strings that end with dollar and have a substring UCLA within it. Then we are basically saying, is the input in this set or not? So that's accepting, that is it's in the set, and rejecting, meaning it's out of the set. And a generalized, so we had spent some time over that. Then a generalization of this is called classifiers. And the idea in classifiers is that we are not looking for a single test. So it's not like just a single set which we are interested in, the set consisting of strings with UCLA, but maybe we are looking for a few different ones. So yeah, a few different categories. So an example would be if, let's say, I'm getting bits, and at some point the bits will end. and I want to say that is the number that we received, what is the remainder, if you think of it as a number, long sort of the set of bits constituting an integer, is it divisible by 4 or not? Sorry, is it, what's the remainder when you divide it by 4? So in that case, there will be 4 possible options. Remainder is 0 or 1 or 2 or 3. And so you can say there are 4 end states in that particular case, as opposed to the 2 in our acceptor. So here it's called a classifier, that we are classifying strings into multiple categories, whereas an acceptor classifies strings into 2 categories, succeeded and failed. In terms of hardware, you can think of that I have inputs coming in. So like, for example, in my UCLA example, the characters could be, let's say, 8-bit ASCII representation of characters. So the characters would be coming in. So each let's say each clock tick, a new character is supposed to be provided by the outside world. And then at some point, the outside world will say, okay, I'm done with, there is a dollar character to indicate that. And meanwhile, what the hardware has to do is it has to provide an output, which in case of a classifier, sorry, in case of an acceptor would simply be 1 bit, and in case of a classifier, multiple bits, but it's basically indicating which categories, pass, fail, acceptor, or which class, in case of classifier, does it belong to. And simultaneously, usually there would be some other signal which would let you see that now I can now the external world can examine the input, because remember, can examine the output, because the input could be arbitrary length. So how do we know that the machine is done? So this ready or done, there would be some way for the machine to say, okay, yeah, now I have decided, and this is the answer. So the specifics of what would happen will depend upon the circumstances. For example, sometimes we may see these machines where the input, instead of coming every clock tick, might be coming together with another symbol which says, okay, there is a valid input on the input. So for example, what often happens is that your hardware runs very fast, like on, let's say, a clock which may be megahertz or hundreds of megahertz, and your input is coming from some sort of a keyboard. So whenever the user presses a key, we take milliseconds, at least, sometimes even more, when we press a key. So what would happen is that a single key press would actually last many, many clock ticks. So in that case, so let's say I was typing and we are doing the same UCLA thing. So let's say I pressed A, B, C, UCLA. Then when I press, let's say, the key B, then the B key would have lasted for many clock ticks. And so we can't design the machine the way we are thinking out here. Now we have to say, we'll examine the input not only when we'll examine the input only at some special moments, like only once during a key press. So you may have to do some further kind of processing of the input to make sure things work. So we'll see some examples later on, but the general concept at the end of the day is that these are machines which are classifying into 2 or more categories. Now, these are interesting. Oftentimes, we are interested in looking for patterns. Like, for example, one place where you find these kind of machines is the hardware which goes into the internet. So in the internet, you have packets of data which go from one machine to another machine. And as they do, they kind of go through these special computers, which are called routers and bridges and things like that. And these machines, as the data are flowing through the network at very high speed, they have to examine and then route the packet accordingly, right? I mean, so let's say if the packet matches a particular string, then I'm going to send it to a different router, and if it matches some other string, I'm going to send it to some other router. So they basically do a lot of bit pattern matching, and that is usually implemented by hardware implementing these kind of state machines, which are classifying things into categories. Since the data rates are very high, usually this kind of stuff cannot be done with software. So there's a hardware implemented directly into chips. Finite state machines directly implemented in hardware that do this kind of stuff. Okay, so that's what we had seen last time. Now, there is another interesting category of finite state machines. By the way, before I move on, any questions on acceptor classifier? Okay. Let's examine another category, which is transducers. So the idea behind transducers is that they don't stop. Okay, their goal is not to categorize the input into one category versus another, but rather they take a stream of symbols on the input continuously, and they are producing continuously another stream on the output side. So and they basically run forever. There is no end state. They never stop, at least conceptually, until you turn the system off, for example. So the idea here is that they're doing some sort of a translation. Like, for example, let's say we consider a task of converting inputs are English text, and the output is the same English text but all uppercase, right? That would be a very simple example, but of a transducer, right? So it's taking one. Or let's imagine another one. It's taking text in one language and translating it into a different language. Or it is doing some sort of a numeric transformation. Like, for example, let's say it's receiving numbers, and then what it does is it takes a running average of three numbers. So like I may be sending, let's say, a whole bunch of numbers, and the output I is the average of input I minus 1, and input I minus 2. So it's kind of doing a running average. So these are all examples of transducers. So conceptually, for every input, there is a corresponding, for some, let's say, in general, for some sequence of input, there is a corresponding output symbol out here. And this kind of stuff is very useful in a lot of systems that are used in electrical engineering also. So like, for example, systems which are designed to do control, like control the, let's say, the motion of a robot, for example, or the speed of a motor, things like that. So what happens is typically sensors measure what is happening to some physical system, and the readings of the sensors come as input, and then the transducer acts as a control system. So it calculates how to then, like, for example, in case of motor, what new value of voltage to apply to the motor so that the motor moves at the right speed, for example. So control systems, communication systems, systems that deal with various kind of media like audio, video, they all make heavy use of these kind of transducers, finite state machines. So let's look at an example. Okay. So this, what we have out here is a machine that whose job is that it should output 1 if input thus far has even number of 0 bits. So what's happening in this case is that I'm getting a sequence of bits, and so the outside world is sending me bits, and at any given point in time, what I want to do is I want the output to say, oh, have we received an even number of 0 bits or an odd number of 0 bits? So specifically, we want the behavior like the following. So I'm going to just draw it out here. Okay, so let's imagine the input that came was like this: 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, something like that. Okay, so we'll start out with output being 0, and then the first 0 came, then it's an odd number. The second 0 came, so first 0 came, so I'm going to draw that the output appears a clock cycle later. So output is 0 when this guy comes. Then the next 0 comes, then we have an even number of 0 bits. So then I'm going to output 1. Then there's a 1, so I skip over it. Just a sec. Then I get another 0. So that means still odd. So I do another 0. Then I get another 0. And now I have an even number. So I output a 1 and so on and so forth. So that's the behavior we want. We want the output to basically indicate, have I received an even number of zeros thus far since power up, since
Professor,
start. Uh-huh.
why does the first one correspond to an output of 0 and not 1? I thought that the ones did not
Oh
change the
yeah,
output.
you are right. You are right. I'm sorry. I'm sorry. Yeah, absolutely. My bad. Yeah, thank you. The other thing I would point out is I'm drawing the output delayed by a clock. That really kind of depends upon whether I'm thinking of the machine as a Moore machine or a Mealy machine. In case of a Mealy machine, the output would come immediately as soon as the input comes because it will impact things, whereas in Moore, it's typically delayed. That's not really material so much as long as we kind of realize that the output is caused by a corresponding input. It may, depending upon the type of hardware, it may appear in the same clock tick or the next clock tick. So that's really a function of that. So let's see whether our state machine is doing that, right? So what's happening out here is we start out in this state S1, and that's basically saying that, hey, I have not received any 0 bits. So I have received, uh, therefore, even number. So 0 is even. So in that case, I guess I will output 1. So I guess you could argue that I had an error out here also, which is if I have received 0 bits thus far, then actually I have received even number of 0 bits. Okay, so if I've not received any bits, then I have therefore received even number of 0 bits. So I guess we start out in 1. Okay, so we start out in S1, and then every time I get a 0, so if I get the 0, I move to state S2, and then I may get a set sequence of ones, so I kind of remain out here. But S2 indicates that S2 says the meaning of S2 is uh, odd number of 0 bits, and the meaning of this guy S1 is even number of 0 bits. Okay, so we basically flip flop between S1 and S2 every time we get a 0, and we stay put in those states as long as we are getting ones. So that's relatively conceptually straightforward. Now the question becomes, how is the output happening? So essentially, if I'm in state
Professor?
S1, yeah, go ahead, please.
So just to clarify, what's the difference between the transducer and the one before that, the classifier? Is it the classifier has one input and multiple select outputs, and this one has multiple, like a stream of inputs and a stream of outputs? Is that the difference?
No, so the thing is that the classifier at some stage ends into a state and stays there, right? Because it terminates. At some stage it would say, okay, I have recognized whether which class it is in, accepting, rejecting, or whatever remainder 0, 1, 2,
Mm,
3, and
yeah.
then it will output. And then even though there will be bits coming at the output of the hardware, because after all it's hardware, but those bits don't necessarily carry any meaning. So the idea is, if you look at the state machine, in the state machine for that UCL example, you would see states like these where I reach that state and I never get out of them, right? Because
Yeah.
I have done the classification.
Mhm.
Whereas if you see the state machine of a transducer, other than other than error handling kind of things, you won't see that because I'm kind of engaged in a translation task, right? So I'm constantly looking for new input and
Oh,
translate.
okay, okay. Okay, I see what you're saying. Right. Thank
But again, do bear in mind that at a hardware level, of course, even the accelerator machines will still have an output, and I mean, still running, and there will be some bit present at the output, but they would not carry any meaning to us. So this concept of acceptor, classifier, and transducer really makes sense at the level of this graph finite state machine that we are talking about, right? That there is state and that we end there. So in case of transducers, you kind of never end. The only thing is sometimes in transducers, you like I briefly mentioned just now, there might be an erroneous situation, right? I mean, I may say that under maybe the input was not allowed to do something, and if I see that, then I go into a terminal state called error.
All right. Okay. Thank you.
Okay. So back to the story out here. So state S1 represents that I have received even number of bits, and state S2 represents I have received an odd number of bits thus far. And therefore, I have to output 1 or 0 accordingly. And this naturally seems to fall into a more type state machine, right? So while I am out here, I would say out. Let's say I have a output called out. So I will say out equal to 0. And here I will say out equal to 1. Okay, because so in this case, it's clearly sort of the way we are thinking of this thing is as a Moore machine. Okay. Okay, so let's look at another example. So here, what we want to do is
Professor. Can you explain why this is a Moore machine? Maybe I missed it, but we're still relying on the next input bit, aren't we?
Well, we are, but at any given point in time, my output is only a function of since state S1, whatever is the bit representation of the state, it unambiguously, if I'm in state S1, output is always 1, independent of the input. So if you think about what the underlying combinational logic would look like, it will only examine the contents of the state register and then compute output from that, right? So to calculate the output, I only need to know the state I am in.
Okay, I see. Thank you.
Right? Whereas in some examples, you might see that to compute the output, I not only have to look at which state I am in, but also what input currently is there. Okay, so that's why. Now, so moving on, another example of a transducer is that I'm getting bits. And the idea is that I want to examine, I want to output 1 if the bits that I have received thus far represent a number that is divisible by 3. Okay, so basically I'm receiving bits. So let's say I receive these bits 0, 1, 0, 1, 0, 0, and so on and so forth. Okay, so the idea is that maybe I should let me see. So this is 5, 10. Yeah, let me form a more interesting example. Okay, let's say I am getting this bit sequence, and I am getting starting from, so time is proceeding from left to right. Moreover, the bits that I am getting, they are basically represent the number as you would normally see. So like if let's say if I am at this point here, let's say, then I have received 0, 0, 1, 1, 0, 1, 0. So I'm going to think of that as a binary number. And I'm going to say is with the first 0 being the MSB and the latest bit I got out here as the least significant bit. And I'm basically going to say that is this number divisible by 3? And the one which I underline. And if it is, then I'm going to output 1. And I'm doing this at every time step. At the next time step, I'm going to examine the new number like this, and again make the same assertion that is the number 0, 0, 1, 1, 0, 1, 0, 1, is that divisible by 3? So at every clock tick, basically I'm saying, let's think of that big binary number that I have received since the start. Is that divisible by 3? Okay, now that sounds kind of interesting, right? That every time I'm getting a bit, like how do I handle it? How do I know that the bits received thus far is divisible by 3? and we want to do it simply, obviously, right? I mean, we don't want to like take that number and run it through some sort of a combinational circuit which checks for division by 3. Okay, that would be too complex. Now, this is where what comes is that one has to be a little bit creative and think at the algorithm level. This is, again, there's nothing about hardware out here. This is about taking the problem specification and coming up with an efficient algorithm for it, right? If I were to give you this task in software, if I were to say, start reading a file and create another file where as you read the file bit by bit, and every time you read a bit, the corresponding output bit should tell me is the number thus far, number represented thus far divisible by 3. So kind of one algorithm would be, I read a bit, look at it as a big binary number, check whether it's divisible by 3. Read another bit, I have another big binary number, I again check. The problem is I'm now doing this check again and again and again, right? Ever larger numbers. Yeah, go ahead.
When you say bit vector thus far, you mean you're reading from right to left, right?
I'm reading left to right.
So you're reading from least significant to most significant?
I'm reading from most significant. Oh, okay. That's okay. Yeah. T equal to 0 is the MSB. Hopefully that helps you. Okay.
Oh, and then you keep on going to the right.
So I'm getting more and more bits on the least significant side. Okay.
Oh, okay. All right.
Professor.
So as time is proceeding, or as I'm going down the file, I'm getting more and more like I'm expanding on the right hand side on the least significant bit side of the number. So
wait, wouldn't that be the most significant bit side if you're adding it to the right side?
No, it would be the least significant, right? When you write a number like 101010, that's the rightmost number has the least significant bit, right? Like in the binary number 1010, this thing has a weight of 2 to the power 0, and this thing has a weight of 2 to the power 3, right?
Okay, I must have understood wrong. It's okay. All right.
Professor?
Yeah, go ahead.
So if you were at t equals 2, you'd have 0, 0, 1, and that would correspond to the decimal digit 1.
Well, that will correspond to the decimal. That will correspond to decimal number 1. But let's say I go to 0011 at t equal to 4, then I have received 0011, and that corresponds to decimal number 3, and therefore the output would be okay.
Thank you.
Yeah. So that's what we want to do, and basically we want to do it without kind of every time I get one more bit, forming another new number, checking it with some sort of something which checks for divide by 3. That would be extremely inefficient, particularly in hardware, because right, because you don't want to do something like a division operator every time you get a new bit. So can I do it more smartly? And like I said, this is really about, given the problem specification, coming up with an algorithm which is hardware friendly. That's really the hardest part in these kind of things. So here we make an observation. So let's say thus far I had received the number 001, and now I get one more bit, right? So getting one more bit is equivalent to saying that whatever number I had previously received, I'm shifting it left by 1 and inserting things, right? So if I inserting the new bit out here. So for example, say I always examine numbers. This is bit position 0, this is bit position 1, this is bit position 2, this is bit position 3. And previously I had received 001, right, thus far, and I had not only received 3 bits. Now I received this new bit 1. So now the number I have to examine is this guy. But that is equivalent to saying that I take the old number, which was 001, I shift it left by 1, and then I add the new bit I got, right? When I'm inserting to the right, mathematically, the operation is equivalent to taking the existing number and multiplying it by 2, and then adding the new bit I got to it. Does everyone agree with that? Okay. Now, the existing number that we had would have been in one of three categories. If I were to divide it by 3, it would either have a remainder of 0, or a remainder of 1, or a remainder of 2. So I will make, and then when I get the new bit, the new number I have will again be in one of these three categories, right? It would either be divisible by 0 or divisible by 1, sorry, have a remainder of 0 or a remainder of 1 or a remainder of 2 when divided by 3. So let's say state S0, S1, and S2 correspond to that the number thus far, the bits that thus far that I received, the numbers they form, the remainder of their modulo 3 is either 0 or 1 or 2. And now I'm getting a new bit. So let's say the number thus far was perfectly divisible by 3. So I would have a remainder of 0. And that's also my start state. If I've not received any bits, that means I've received 0, and that's obviously divisible by 3. Now, if I was divisible by 3, if the number thus far was divisible by 3, and let's say I got a 0. So that would be equivalent to saying that I'm shifting it left, I'm multiplying it by 2 basically. So I'm taking the current number, which was divisible by 3, I'm multiplying it by 2 and adding 0 to it because I got a 0 input. But if I do that, then I will remain divisible by 3, right? If I have, let's say, the number 21, if I multiply 21 by 2, I get 42, and I got the 0 bit, so 42 plus 0, 42, still divisible by 3, right? So if if the number thus far was divisible by 3, then getting a 0 will keep it divisible by 3, and getting a 1 would make it modulo have a remainder of 1. So I will move to state S1. If I was in state S1, that means that my current number thus far, if divided by 3, would have yielded a remainder of 1. Now I'm multiplying my current number by 2. So that means whatever the current number was times 2, if I were to divide this new number, this multiplication of 2 by 3, now my remainder would be 2, right? Because originally remainder was 1. So for example, if the number was 22 thus far, multiplying it, that has a remainder of 1. If I multiply it by 2, I get 44, and that has a remainder of 2, right? So remainder gets multiplied with that. And the new bit I'm getting, if it is 0, then that means the new number would have a remainder of 2. And if the new bit was 1, then that means I will have a remainder of 3. So in my example, if the current number was 22, so and let's say that consider the cases if the new bit is 0 and the new bit is 1. So this thing had a remainder of 2, right? So 22 modulo 3 is 1. Sorry, it has a remainder of 1. If I got a bit 0, then that would mean it's 44. And if I got a bit of 1, that means it's 45. And so 44 will have a remainder of 2, whereas 45 would have a remainder of 0. Which means if I am currently in state S1 and I get a 0 bit, then I should move to state S2, which is what we are doing out here. I'm moving to state S2. On the other hand, if I am in this S1 and I get a 1 bit, then that means the new number is divisible by 3. So I move to state S0. Does everyone get this part? If I have a number x, and if x modulo 3, x remainder 3 was 1, then 2x plus 0 modulo 3 will be 2, and 2x plus 1 modulo 3 would be 0. And therefore, it corresponds to moving to either state S2 or state S0. Okay. And then finally, if I'm already in state S2, that means x modulo 3 is 2. If I get so 2x would have either So if I do a 2x of that, so since the original modulo was 2, so it would either become 4, which is same as 1. It will become 4, which is same as 1. And now if I'm getting 0 bit, that means modulo will be 1. And if I'm getting a 1 bit, that means the modulo will remain 2. So that, which is why what you're seeing, that if I'm in S2 and I get a 1 bit, I remain at modulo 2. So I remain at remainder 2. And if I get a 0 bit, I move to remainder 1. So in this case, as you can see, every time a bit comes in, I'm basically doing some very trivial operation, and I'm keeping track of, is the number thus far divisible by 3? And what it required was this thing, the thinking about like, how do I formulate that problem? Like, how many states do I truly have thus far? And the key insight here is that the state here corresponds to the remainders, and that's what we have to do. Now, of course, I make it sound like, in retrospect, everything sounds simple. If I were to face this kind of a problem afresh, would I have discovered this algorithm without knowing what I know? Who knows, right? So the trick out here with these kind of problems is kind of experience with algorithms, right? I mean, it's often hard to come up from scratch with these things. Exploiting your knowledge of arithmetic, exploiting your intuition. So like, for example, let's say if we were to modify this problem and say, instead of divide by 3, what would happen if I were to ask you output 1 if the number thus far is divisible by 5? So now, since you have seen this problem, your first instinct should be, I'm going to try now with having 5 states corresponding to modulo 0, 1, 2, 3, 4. And then I'm going to come up with these rules, right? I mean, every time I get a new bit, it is 2 times the current number x plus 1. But now you have to think about what is happening to the remainder, given that I was in state S0 or S1 or S2 or S3 or S4. And so again, exploit arithmetic. Now, so once you have seen this, you should be able to solve similar problems where the division is by some other number, okay? For example. So this is coming up with the state machine is really coming up with an algorithm, okay? But an algorithm which is optimized for hardware, because implementing the state machine in hardware is like super simple. Whereas if we were to do it with the software mindset, what we would have done every time is we would have done, oh, my current number is x, I get a new bit, I compute 2x plus 1, and then if I'm programming in, let's say, C++, I would have immediately done, oh, 2x plus 1 modulo 3, what is the answer, right? So in software, we don't think about that the percent operator in my programming language. I mean, it's basically just a simple operator. It's an instruction in the machine. But when you are thinking with a hardware mindset, and designing a chip or an FPGA or something like that, then there is a huge difference between a percent operator, because a percent operator requires division, versus kind of applying some smarter algorithm to it. So any question on this slide?
I'm a little bit confused as to how a bit vector of 1, 0 is divisible by 3. Can we just go over that one again?
Okay, so so if I received, so let's say I received so I'm starting with nothing. So you tell me the input, and then we are going to work through. So what are the bits we are receiving? Tell me that.
First we receive a 1, and then we receive a 0.
Okay, so we start out in state S0. Since we have not received any bits, so the number is 0, so it's divisible by 3. Then I receive a 1, so I get to S1, and that says that when the number I have received, if it's modulo 3, it is 1, which is true, because if I have received 1, that means I've received the number 1, right? That's a single bit number, and therefore it is 1. After that, I received a 0 in your example, so I reached here, and so the number I have received thus far is 1, 0, which is 2, and 2 modulo 3 is indeed 2. Right? So if I once submit the second bit, I have received the number 2, right? And therefore the module is 2. Let's say after that I were to receive 1, right? So 101 is 5, and 5 divided by 3 would 5 modulo 3 is 2, So, and that's the behavior we want. And see again, if it is 1, I stay put out here. Let's say after that I got a 0. So now the new number I have is 8 plus 2, 10. 10 modulo 3 is 1. And indeed, with 0, I move to state S1. Let's say I get another bit, which is 1. Then the new number is 16 plus 4, 20 plus 1, 21. And it would indeed move to S0, and indicating that modulo 3 is 0. Make
I
sense?
understand. Thank you, Professor.
Sure. Okay, so I wish I could tell you how someone who originally thought of this came up with this, but clearly a deep insight into the problem domain is crucial with these kind of problems, right? I mean, don't just read the specification kind of as is and then kind of directly attempt to translate it. Think about the properties that exist, right? In this case, we're talking about numbers and division and things like that. So you need to kind of exploit that background knowledge that exists. So now, having seen that, anyone have a question? Okay. So now we are going to think of finite state machine in a more formal manner. Okay, so we kind of gave some examples and drawings and all. So you can think of finite state machine itself as a mathematical object. And it's a mathematical object that consists of 6 things. So some of you may have heard the term tuples in your programming classes, but tuple basically refers to, think of it like sort of 6 things bundled together. Okay, so it's a sextuple. Okay, and it consists of 6 things: sigma, uppercase sigma, uppercase gamma, s, uppercase s, s subscript 0, delta, and omega. So what are these things? Okay, so sigma is an input alphabet. It's basically saying it's a set of symbols that the machine receives on the input. Okay, so for example, in this case, the sigma was just the set 0 and 1 because I had only 2 allowable inputs. In my UCLA example, it were the characters of the English alphabet and the special symbol $, for example. So that's the big set sigma. The gamma, sorry, it's not gamma, it's lambda. So it's the output alphabet. It's the set of symbols that we are outputting. Now again, in our previous example, it's just 0 and 1. So that's the set. So oftentimes, in kind of in the examples that we will have, the output symbol could be just that, but it could also be things like speed setting of a motor. So maybe motor has 5 settings of the speed, in which case the output symbol would correspond to speed 0, speed 1, speed 2, speed 3, speed 4, for example. So it could be something which just carries some meaning. Then the set S is the set of states. So it is the set of states, like in our example, there were 2 states, well, in this one, 3 states, S0, S1, S2. These states just have names. At some later stage, we are going to talk about that how do we represent these states in hardware. Okay, of course, the states will eventually have to be mapped to bits. So we have a problem of like, what's the bit representation of these states? But at this conceptual level, you can say that I have states with represented by some symbols, right? I mean, that, or divide by 0, divide by 1, divide by 2, or like in our UCLA example, I was calling state to be start, found U, found C, found L, and success. Okay, so I'll have a set of states. That's the S. Okay, so we have covered these 3. Then the little S0 is the start state. Okay, it's the initial state. So little S0 is a member of the set S. Set of states. Now, if you have a proper, in almost all cases, you will have a unique start state. Sometimes you may have systems which could start in one of more than one state, depending upon how they are being used. Okay, so there may be more than one start state, in which case S0 could itself be a subset of S. And in that case, really the state machine is referred to as being non-deterministic because its behavior depends upon where you are starting. In our cases, so for example, let's say if the hardware powers up, then the state vector, the state bits are arbitrary. So if you don't do anything special, then most hardware, when they start up, they actually could start in any state. So usually in hardware, we provide a reset signal to force the hardware immediately into a particular state so that we can have a deterministic behavior. It turns out in computer science, there are valid reasons why people like to think about non-deterministic FSM also. We would not worry about them out here. Then delta is a function. What it does is it takes a state and it takes an input. So it takes what state I am in and what is the next input symbol, that what's the input symbol I received. And then it tells me which is the next state, right? So it's saying this is the current state. Gamma is the input. What we got. And this is telling me what the next state is. So it's taking current state and input and then telling me what the next state is, right? So it's a function which takes two values, the current state and the input symbol, and then tells me what the next state is. So essentially, this tells me what the edge is in my finite state machine graph. And finally, omega is the output function. It is telling me what the output is. And depending upon milli or more, the output function behaves slightly differently. So if I have a milli state machine, then remember in a milli state machine, the output depends upon both the state and the input. So in that case, omega takes state and input and tells me the output, right? Takes what state I am in, what the current input symbol is, and it tells me what the output symbol should be. What kind of function do you think if it would be if it is a Moore FSM? What would it map? So omega.
Would it just be the S because you're just worried about the state?
Exactly. Got it. Okay. So in case of Moore, it would look like that. So in case of Moore, that's the function. Okay. Great. So when we often say that describe a finite state machine, you can say that really these 6 elements are what we have to present, right? I mean, if to completely and rigorously describe a finite state machine, we have to specify these things. All these diagrams we are drawing and stuff like that are really kind of different ways of representing this 6 step, right? I mean, I can indeed describe a state machine strictly as this kind of in terms of these things, in terms of basically input alphabet set, output alphabet set, the set of states, the initial state, and 2 functions, right? That's what it takes to describe a state machine. That graphs we are drawing is a representation of it. The hardware we were making for sequential machines is another representation of it. But deep down, this is what fundamentally an FSM is about. So now, what we are interested in is that if we saw that from a problem description, we can get to those graph-like things, right? You have to think about it, but at least you have seen some simple examples. But our goal is not to stop there. Our goal is to really go all the way down to hardware, right? So in some senses, our job as a designer is to take this English language description of a problem and then eventually end up with a sequential system for doing it, right? But and the hardest step in this is from that description of the problem, coming up with a representation of the FSM, typically that diagram, but maybe also code in Verilog, for example. After that is mechanical, okay? But we are going to walk through that. So mapping FSMs to sequential circuit is the next thing that we are going to look at.
Professor?
Go ahead.
Could you explain the delta again real quick? What do you mean by that?
So think of delta as a function. Okay, so there's a function. there's a function delta. It takes two values. What my current state is. So it may say, hey, your current state is S0. And what my input is. Like it may say input is 0. And then it will tell me what is the next state. So like, for example, if I go out here, so let's see what head I picked out here as my, I said I'm S0 and 0, right? So it would say S0 and 0, the next state is S0. So this function lists for every possible current state and input what the corresponding next state is. So you can think of this function as a table where it tells me what. So we'll see some examples of it, but you can.
Oh yeah, I understand what you're saying. Yeah, and then the S0 is just like the starting point where, like on the previous example,
yeah,
you started off.
Or like if it was S1 and the input was 1, then well,
whatever it was.
1, it goes back to S0, so 0, right? So it basically, think of it as a function. It's a mapping. It's a mapping from the cross product set S cross sigma to the set S, right? So its domain is the set S cross product with sigma, and the range is S.
Yeah, I see. All right, thank you.
Okay, so now mapping to this process, this mapping process. So kind of, if you kind of step back and say, what do I need to do? So firstly, you are going to be given some sort of a specification, behavior specification, like what should the system do? And the first thing, and this is really kind of, to me, this is the hardest part. And this is where you should spend time, okay? Because if you get this wrong, then everything else is wrong after that, which is coming up with a strategy, right? How am I going to approach the problem? What's the algorithm, right? That's really what this is about. What is the algorithm? And not just any algorithm, but one which is efficient when we'll map it to hardware. So you need to have that intuition on it. So it should not involve complex operators, like we were able to do that remainder 3 without actually using division at all. Then once you have the strategy, then you are going to write down the state machine. And there are tools to help you do that. So I had shown last time a tool called FISM, but there may be others. But FISM in particular is meant for state machines mapping to hardware, but there are possibly others that one could use. So then at that stage, I will have a diagram like this, right? This kind of stuff. The one thing missing out here is we don't know what bits represent the states, right? I mean, I know I have 3 states, and therefore I can say, hey, I need at least 2 bits, right? Because I need to represent 3 states. But what should be the representation, right? Is S0 mapping to 0, 0? Is S1 mapping to 0, 1? Is S2 mapping to 1, 0? Or do I have some other mapping? We saw earlier in the course that when I give you some things to represent, there are many ways. Maybe I can do one-hot coding. Maybe I can do some other type of coding. So we face that problem out here. So that's called the state assignment problem. And believe it or not, there are algorithms to do it, which kind of look at the structure of your graph and then try to come up with a good state assignment, one which will yield efficient hardware. Okay, there are 2 elements to our hardware: how many flip-flops I need, and how complex our combinational logic is. So sometimes you may face with a situation that, maybe I can need more flip-flops, but my combinational logic becomes super simple. Or the other way around, that you may say, okay, my flip-flops are very expensive, so I'm going to keep very few flip-flops, minimum number necessary, and take the hit on combinational logic. Anyway, be what it may, once you have done that, now you have, after that, the process is essentially one of translation, and we're going to see that shortly. So there is a manual approach which we are going to do, which is you form what are called as state transition and output tables. Okay, so we form a kind of something which looks like a truth table. We already saw that actually earlier on. Remember where we had seen this table which had the input and the current state, and then on the output side it had the next state and the output. We had seen that last lecture. So we formed that table, but it's pretty much a mechanical thing to do. And then we design the combinational logic. So this part is pretty traditional. We have kind of seen it basically. So once we have that table, then it's just a matter of the Carnot map type strategy. Or alternatively, once we have that, once we have done the state assignment, we can write it into Verilog, VHDL, one of these languages, and Swim happily does it for you. For example, it can generate Verilog, and then you feed it into some programming, some tool. So those of you who are in the honors class, we have seen Yosys, but there are companies which make industry standard products. So like the most famous one is a company called Synopsys. So they make these like super expensive tools, which among other things do these kind of things automatically. And at the end, you basically get a wiring diagram consisting of gates and flip-flops. And then you feed them into another set of tools to get your chip or FPGA or whatnot. So that's a sequence of things. We are going to spend some time now. So we have seen kind of examples of behavior to strategy to state diagram. Now we are going to spend our time looking at what happens on this part, really, this part. We are going to spend our time here.
Professor?
Okay. Yeah, go ahead.
Earlier, a few slides ago, when you talked about how for the Mealy model, gamma is a cross product of S and sigma. Could you clarify what you meant by cross product, or did you mean like Cartesian product?
Oh, Cartesian product of two sets.
Okay, thank you.
Okay, sure. Every possible combination of one input from one element from S and one element from sigma. Okay. Okay. So so divide by 3 FSM. So actually, the reason I started the lecture late was as I was preparing for it, I noticed that I had messed up the slide. So actually, I had to update the slide. The updated slide is available on Piazza, but not yet on CCLE. So if you printed out previously, you would see some subtle changes here in zeros and ones. Okay, so my apologies for that, but I must have been sleepy when I was preparing this originally. So anyway, so the idea out here is that what we want to do is we kind of want to create a state machine which is kind of doing divide by 3 operation, but basically what it is doing is the following: that every time it sees a sequence of 3 ones, then it's going to replace it by a single one. Okay, so essentially it will, the only time it will output a 1 is when it sees a sequence of 3 ones, then it outputs a 1. And there is again a clock delay out here because we are thinking in terms of a Moore machine out here. And likewise, it sees a sequence of 3 ones and it outputs a 1. It sees a sequence of another 3 ones and then it outputs a 1. This one should also be green. Okay, this should also be green. Okay, sticking with my notation. But anyway, that's the functionality we want. So the state diagram for it. So the first thing we have to see is that, how many states do I need? That very first step, right? So when we are starting out, I have seen nothing. So we'll just call it 0. And then, so it's kind of like a pattern matching thing of sorts, except that we never stop out here. We are continually on the lookout for, once we have received a pattern of 3 ones, then again, I'm going to look for the next such pattern. So what we'll do is we'll think it in terms of, have I seen 1 1, 2 1s, or 3 1s? So we are going to call those things as state first, second, and third. So if starting out from state 0, if I see one input to be 1, I move to the second state. Then if I receive another 1, I move to second state called second. And then I got another 1, I move to the state called third. And at that point, I output 1. So usually what is good here is, what works for me at least is I think of the base case. right? So in this case, as long as I was receiving 0, I stayed put in 0. So that's this self loop. And then I got 1, 1, 1. I moved out here. And now let's see all the other cases. So if I was in state 1, I had received one. Actually, I think my time. Just a sec. Yeah. Let me. This thing is not doing. This is what we want to do.
Professor,
Yeah.
would this
Just
finite state machine be outputting every time we found 3 ones?
every third one I have to output a 1. So this is what I'm going to be doing. Okay, so I'm going to be 0, 0, 0, 0, 0, 1. So this is a third one. Then again 0, 0, 0, 0, 1. This is a third one. Okay, so first, second, third, then 0, 0, 0, 0, 1. Okay, that's what we want. So every time I have, so every third one with intervening zeros if necessary, I'm going to output a 1. So I'm basically, think of it like the number of ones in my input string. And in the output string, I will have a factor of 3 fewer ones. Like if my input string had 6 ones, then my output string will have 2 ones. So that's what we are doing. Okay. So actually, I'm going to fix this timing diagram. I think I still managed to get it wrong, but that's what I want. So in this case, the one which I have written, I started with 0, 1, 0, 1, and then 1 out here. This one, let me change color. This is a third one, right? Because I have seen 2 previous ones. So on this third one, I'm going to output a 1. Let me clean up the diagram out here. Just give me a sec. So that's the third one. So for that one, I will output 1, and that's what you see out here. Then again, I start counting how many ones I have received, and so I skip over this one, I skip over this one, but the third one, so this one. Okay, again, let me clean it up. So that it's clear that what we are talking about. So this is the third one, which again I'm interested in. Okay, and likewise, yeah, go ahead.
If you look at the first one, like up to that third one, that number is not divisible by 3, is it? Because it's 8 plus 2 plus 1, which is 11.
No. It is not dividing the number. It is dividing the number of ones by 3. I think that's what I should have called it. It's not dividing the number by 3. It's dividing the number of ones by 3.
Wait, are you trying to, this might clarify, are you trying to define, like find out the manual approach for the divide by 3 example that you were doing before previously?
No. Again, so follow through the example, right? I mean, it's dividing the number of the count of ones by 3. So in the original string, I had 0, 1, 0, 1, 1. Once I receive a third one, I output a 1. So I want the number of ones in the output to be 1/3 of the number of ones in the input.
Oh, okay. That's just how you define the. That's how you define it.
The number of ones. Yeah, So I think a better name for this thing is divide the number of ones by 3. Okay, or the count of ones. Okay, and the strategy we are doing is that every third one we are going to output a 1. Okay, so it's kind of like, I mean, I have a population of something, and I want to, it has some whatever apples in it, and I want to pick 1/3 of the apples. So my strategy is that as I walk through this thing, every third apple I pick up. That's what we're doing. So every third one I pick up.
Professor?
Yeah.
So let's say we already output a 1, but then in our input, let's say we have a finite bits of input, but we found an extra 2 1s at the end, so it's not enough to like output another one. So it would just be a 0 0 at the output.
Yeah, exactly. Yeah.
Okay.
Yeah. So we are always picking the third one. Yeah.
I think there's someone in the chat asking you a question, and he said his mic is not working.
Oh, okay. Oh, how to define the two functions? Okay. So the omega function is the set of symbols that constitute the output. Okay. So in this example, I have two output symbols, 0 and 1. So the sigma in this example is a set 0, 1. The gamma is the hang on a second. Let me make sure that I don't screw up the notation. Not sigma. Yeah, I totally messed up. Sorry. So sigma is the set. Let me make a clean slide out here. So just give me a sec. So in this preceding example, now what is state? I have 4 states out here, right? So they are called 0, first, second, and third. So that's literally what I have. They're just names. Right? The initial state is 0, is 0. It's element 0. Then I have to define two functions. If you go back to our definition, I have to define the delta, which is a state transition, and omega, which is the output function. So okay. So I have to define delta, which is a transition function, right? So there are many different ways one can write functions, but we can think of delta as a table, which takes current state, takes input. What happened? Now, I have 4 possible current states and I have 2 possible inputs. So I have 8 possible cases. Too many of them for me to draw out here, so I'm not going to do write out here, so I'm not going to do all of them. But let's say I'm in state 0 and input is 0. State 0, input is 1. State first, input is 0. State first, input is 1, right? So now, if I'm in state 0 and the input is 0, what is the next state? Well, I stay in state 0, right? Self loop. So I would say 0. If 0, we get a 1, next state is first. And first, if the input is 0, you see we stay out here. Again, there is a self loop. So this is first. And then I move to second, okay. And so on and so forth. There will be total of 4 times 2 equal to 8 entries. Right? So the domain of this function, I'm sure you guys have done some set theory course, right? So the reason we write that notation out there, this is the product of the two sets. So we take one element from S, one element from sigma, and then define what the output is. So since S has a size, S has 4 elements and sigma has 2 elements, so there are total of 8 possibilities. And so I can write a table which corresponds to each one of them. That is my function, transition function. In mathematics, every function can be represented in a table like this, right? Because every function takes a set of values, takes an element from a set, and then maps it to an element in, it takes an element from my domain set and outputs into an element in my range set. In our case, our domain is the set S, that's this, and my range set is the set S. Okay. So hopefully this explains. And then finally, we had one more function, which is the delta function, which tells me what the output is. So again, you can think of the delta in the same way. So let me.
You mean omega?
Oh yeah, sorry, omega. You're right. Yeah. So the omega function, it maps. So depending upon milli or more. So in our case, this machine is actually a more machine. So it maps S to what am I calling the output set? Yeah. So this set. So again, I will have a table which would correspond to 0. So in this table, I have only 4 entries: 0, first, second, and third. And I guess the outputs are 0, 0, 0, 1, right? If I get it right. Yeah, 0, 0, 0, 1. So that's my omega function. Okay. So that's what's going on out here. I can express this particular state machine in terms of that. So designing FSM, I mean, you can either write it in terms of you can either write it in this diagram, or equivalently you can write a set. Okay, these sets and functions. Okay, so unfortunately my timing diagram here is messed up, so I'm not going to go over that. I'm going to put the corrected slide, but they're basically showing what's happening at each clock tick. But I'm going to fix this. Okay, so and therefore my animation slides are all messed up. Okay, then what happens is that in this process we basically draw this. If we were to go through the process, we will write it out in FISM, and actually in in one of the problems that we will ask you to design something in FISM like this. Okay, so that you get experience on how to write it. So in this case, so you express in FISM. This does not correspond to our current example. Then FISM lets you map to Verilog, and then you feed the Verilog into a tool, and then you will get a netlist of gates. This is a netlist of gates. Okay, so that's kind of the automated path, and then so you basically end up with a set of gates. So so these tools help us a lot. Now, so I'm going to skip through these things, and then eventually, again, like if one were to be using these tools, you can take that wiring diagram, that netlist of gates that is produced, and then simulate it and see whether your hardware works correctly, and before you ship it to an FPGA or send it to fabrication. So that's kind of the process, but now let's walk through the manual portion of this process in context of an example. Okay, so our example, this is from the book. Is a traffic light controller. Okay, so finite state machines get used quite a bit in like automation, factory automation, and these kind of things. In this case, it's some hardware which is controlling traffic lights. So what we have out here is a crossroad, and it's kind of like a smart crossroads where there is a main street which is running north-south, and then there is a side, cross street, where what we do is, because we want to get, we don't want to needlessly cycle through the traffic lights because there's very little traffic in the crossroad. So we basically want to prioritize the flow of traffic on the main road, but then we put sensors to detect arrival of cars. So on the east side and the west side, I have 2 car detectors. So, on the roads, you see those kind of embedded in the road, kind of these magnetic sensors, and when your car goes over it, detects. They're also often used for counting cars and all. So it's some sensor like that. Okay. So the idea is if the car comes over the sensor, then kind of the sensor becomes active. Outputs are 1. So what we do is we take the outputs of the 2-car detector and we feed it into an OR gate so that we get a signal called car EW, which basically says there is a car on the east-west road. Okay, we don't know whether it's a car heading east or a car heading west, but the idea is that there is a car. Okay, so at that point, the idea would be that we will turn the green lights on in the east-west direction, and of course the red light on the north-south direction to let this car through. Okay, and then again after a bit, we'll switch back to the north-south. So that's the behavior we want. So we want to design a piece of hardware. The only one input from the outside world is the car east-west. And then there's a reset so that our system starts in a sane state. Like we don't want it to start with all lights green, for example, right? So we want to start in some good initial state. There is of course a clock and lights. So we really have only 6 lights because the lights facing east and lights facing west, they are the same, and likewise lights facing north and south are the same, right? So we basically this pair of light is one pair of light is basically 3 lights, and this is 3 lights, right? So whenever so there are 2 sets of light. Okay, so that's why we have a total of 6. Total of 6 out here. Okay. Any questions on the problem specification before we move further? Okay, and just to make sure, this is our detecting sensor.
Professor?
Yeah. Go
So
ahead.
the 6 in this diagram isn't the number of bits, right? It's just the number of lights.
It's and our, I guess I'm implicitly thinking in terms of that I'm sending 1-bit signal to turn a particular light on or off. But you are right that I shouldn't perhaps make that assumption. So I should simply say 6 lights. So we are absolutely right. How we encode it would be different. So at this stage, you think of there's 6 lights.
Professor?
Mm-hmm.
Just to clarify, what do you mean by the transition states? I think it was I think it was a part of the previous one. Like, what do you mean by transitions?
These edges, these are transition, right? Like this transition.
Oh, okay. All right, thank you.
Okay. So, so if the problem spec is clear, let's try designing it. Okay. So now the spec is still not full. I have not described to you how the light should behave, right? I mean, of course, from our prior experience, we have some intuition that some of the things that it should do, but we need to spell it out. So first thing we say is it should reset to green in north-south direction. So when we start up, after we reset the system, we want basically, remember I said that the north-south road is kind of a main road. So we are going to make that green. And then we are going to define some rules. We are going to say if light is green or yellow in one direction, the other direction must be red, right? I mean, that makes sense. A light must be yellow when changing from green to red, right? So we don't want to suddenly change from green to red. You want to go through yellow so that the drivers coming in that direction get a little bit of warning. If there is a car waiting on east-west, then east-west should become green before returning to green for north-south. So the idea is that my sensors tell me that there is a car on the east-west segment, then I'm going to make the light on the east-west green, and of course, therefore, light on the north-south red. But before doing it, we go through a yellow stage. So right, we'll turn the north-south right yellow, then north-south red, and east-west green, right? That's what we will do. So that's the set of policies we have, and we are going to basically assume that we are not going to worry about how much time we spend in these things. Like maybe just think in terms of like a single clock tick is sufficient for us. Okay, so that detail we kind of abstract over. In real life, there are also timing requirements on how long should the right light be green and stuff like that. So you'll probably need some timers and all. But for now, let's ignore those parts. So that's what we have. So let's see how we will how we'll design these. Okay. So remember, our finite state machine is specified by states, inputs, outputs, and that those different functions, right? The start state is already defined for us. So if we think about the states, they're really, because of the restriction that if I have green or yellow in one direction and the other direction must be red, then I really have 4 possible states, right? One state is north, south is green. Another state is north, south is yellow. And implicitly in these 2 states, east, west would be red. And then east, west is green or east, west is yellow. And implicitly north, south is red. So there are 4 states out here. Okay. Then what about inputs? Well, I have 2 inputs out here, right? There is the SAR the east-west signal, which is coming from the sensor system. And then we have the reset one. So car east-west is basically telling us, is there a car on the east-west road? And the reset is telling me return to the initial state. Then finally, I have the, I'll have the inputs. Outputs of the lights. And this is where I guess to answer the question that someone had, that what that 6 represent. So essentially, we are assuming out here that my traffic light signals are 1 hot, 2 3-bit 1 hot coded number. So essentially, remember, I have 2 clusters of light. Cluster 1 has a red, green, yellow, and cluster 2 has a red, green, yellow. And within that, I'm going to assume that we have 1 hot coding. That is either red is on or yellow, either red is on or yellow is on or green is on in cluster 1. And likewise, one of them is on in cluster 2. So that's a perfect candidate for 1 hot coding. So that's what we have done out here. So for example, in this case, I take, if I have this symbol, so that's, so the idea is that we have green, yellow, red, and for north, south, and for east, west. So essentially, I have a vector of 6 where first 3 bits form 1 hot coding for north, south, and the second 3 bits correspond to 1 hot coding for east, west. So this vector 1 0 0 0 0 1 basically says north, south, green, and east, west, red, right? So this bit says north, this bit corresponds to this, and the last 1 bit corresponds to this. Likewise, 0 0 1 0 1 0 corresponds to north, south, red, so north, south, red, and east, west, yellow. So those are just a couple of examples, but that's my encoding, okay, that we have decided. So that was the next level of refinement we have done there. Now comes the part about how do we draw the state machine. So remember, we said there were 4 states, right, corresponding to the 4 possibilities. East-west is green, east-west is yellow, north-south is green, or north-south is yellow. So that's how we're going to name the state. So this state GNS means is green, north-south. YNS means is, so that's kind of the meaning of the state. And yellow, north-south, green, east-west, yellow, east-west. Okay, so 4 states. And then once I have those states, this the status of lights are clearly decided at this point. If I have green, north, south, then east, west has to be red. So that means my output will look like this: 1 0 0 for green, north, south, and the 0 0 1 is the red for east, west. Yellow, north, south would be 0 1 0, and then of course it would still remain red in east, west. Green, east, west, similar coding, and yellow, east, west, similar coding. So that's my output, right? These are the, this is the output to light. Okay, Shin.
Wouldn't the state machine produce a green light 1 car at a time for the east-west?
Yeah, it will.
Okay.
Yeah. So, Yeah, this is obviously a super simplified traffic controller, so don't subject it to real life expectations. It would be one car at a time. Yeah, and I guess it kind of makes sense because what you still, I mean, intuitively you can say, the east-west is lower priority. So I'm going to let the car through, but I don't want a surge of traffic on east-west to sacrifice. Okay, so that's
Professor?
good observation. Yeah, go ahead.
Could you clarify physically what the reset input is representing in this example?
So reset basically means I want to go back to the reset state, which is reset to green in north-south direction. So usually the purpose is right after power up, we are going to reset the hardware so that it starts out with green light in north-south direction, and of course red in the east-west. But anytime reset comes, we want to move to that state. So in our example terms, anytime the reset comes, we want to move to the GNS state. So this is my, this state, GNS, is my start or slash reset state. So anytime I have a reset, I go there. And so if that's why you notice, like if I'm in GEW and reset comes, I move to GNS. If I'm in YEW, the star means anything. So from YEW, I will always move to GNS. So that's why it doesn't matter. But like, for example, if I'm in YNS, then again, reset comes, I move to GNS. So anytime reset goes high, I move to GNS. And of course, at power up, usually there will be a reset. So I'm going to start out here. So actually, in terms of our earlier notation, you can say that this, I should actually draw the state with a double circle because it's the start state. So, okay, so now we have the states. Now let's talk about transitions. So we are in the GNS state, let's say. So north-south lights are green. And I'm going to stay in that state as long as either reset is high or there is no car on east-west, right? So what this expression is saying is no car on east-west or reset, right? In either one of these conditions, I'm going to stay put in GNS. If there is car on east-west and there is not a reset, right? So if my sensors are telling me, hey, there is a car and I'm not getting the reset signal, then I have to eventually turn the green light on. But I can't just turn the green light on immediately on east-west, right? So I'm going to move to yellow north-south. And then as long as reset continues to be low, then I will go to green east-west. And again, next time instant. So I'm basically operating on every clock tick out here. So hopefully my clock ticks are not megahertz because then I would be spending very little time in these states. So I guess implicitly the idea out here is that my clocks are probably super slow, like seconds. Okay. But anyway, after green east-west W, I will go to yellow east-west, right? And then I will finally go back to GNS. Anytime a reset comes, I immediately go to GNS. So that's the transition. Super simple, very simplified, almost useless traffic controller, but kind of for illustration purposes, it does the job. In real traffic controllers, there are a lot of nuances, right? I mean, how much time to spend in yellow time, what's the minimum green, and so on and so forth, right? There are all sort of requirements, probably the government standards imposed, but we don't have any of them, right? We are spending exactly one clock tick in YNS, one clock tick in GEW, one clock tick in YEW, and sort of going back. I guess we are assuming that my clock ticks are slow enough so that the car actually gets to drive through the intersection, but all those are abstracted away out. So questions at that, yeah.
When you're transitioning directly from GEW to GNS, wouldn't you want to go through like the yellow state on the east-west road first, or just are you ignoring that?
Great observation. So for reset, we don't obey that. If it is reset, we immediately go to it. But yeah, I guess so. What you are saying is, probably it would be more sensible to have this as reset. And I guess you are right. That one should perhaps that would be a better design.
Okay,
But,
well, I mean, it just depends on the design specification.
yeah, it depends on the design. So in this case, the idea is so this would be the alternative design.
And then what are you representing the star as? That was my other question.
Star means any input, unconditional.
Oh, okay, unconditional. Okay. Because by default you want to keep the north-south road on, so by default.
Yeah. So in FISM, in my previous notation, I was using 1. Book uses star, but kind of the idea is this is a default transition. You just take that.
Oh, okay.
Okay. So now we have our state machine. Everything is specified except for one thing. What are we still missing? Anyone? Someone sent something on chat. Okay, that's the answer. Okay, so what we are still missing is what is the bit vectors for the states, right? I mean, remember, the state has to be stored in the state register. So I need to assign it some bits. I need to say GNS is represented by these bits, YNS is represented by these bits, right? We still haven't decided that. I need at least 2 bits because I have 4 states. But maybe I can do a different, maybe I can use more bits and save on hardware somehow. So we'll see that, how to do it. So by default, okay, I guess I've already done this. Okay, so we've already talked about this. So, okay. I can draw this stuff again in FISM. Not going to spend any time out here. Okay, so now let's see how we proceed with this. Okay, the manual process. So I have my state machine, which we drew. And in this one, for sake of simplicity, I am ignoring the reset. Okay, so I've removed every mention of reset in this one. And the reason often is, remember the goal was that anytime I reset, I just go to GNS. So usually that can be handled outside my main state machine, because oftentimes these hardware flip-flops, they come with that reset input, right? You saw that in Logisim. So what I can do is I can just tie the reset signal to the reset input of all my flip-flops, and then they will immediately go to all zeros, right? All the flip-flops will get reset. And then what I can do is I can make sure that GNS corresponds to all zeros. Okay, I could do that. Okay, so oftentimes you would see that reset is kind of ignored or is kind of treated separately. So, but here also partly just to simplify the example. Okay, so we only have one input now, car east-west signal, and otherwise, so my state machine looks like this. So again, reset ignored. Okay, just imagine that somehow automatically reset is happening. So now what we do is we make this table, which tells me 2 things, which is what is happening when in the current state, and given the input, what is the next state and what is the output. Now this is a Moore machine, so my output only depends on the current state, right? So if I kind of for a moment, if I ignore the next state columns, then given the current state GNS, my output is 100001, where it was the lights for GNS and lights for east-west in that order, right? So it's saying green for north-south and red for east-west. So those are the outputs out here. Okay, so this one. So the output corresponding to current state is just literally copied from the state machine. And then I have the next state. So now the next state transitions depend upon the inputs. So I have 2 cases for next state. If the input car east-west was 0, or if input car east-west was 1. And so if my current state was GNS and car east west was 0, then I stay in GNS. So that's what we see out here, right? So this basically corresponds to that loop. If on the other hand car east west is high, then I take this transition and move to YNS. For all the other current states to next state, car east west doesn't matter. So the two entries are the same, GEW, GEW. So from YNS, we move to GEW, irrespective of the input. From GEW, I move to YEW, irrespective of the input. And from YEW, I move to GNS, irrespective of the input, right? So that's what it looks like. So now I have my both the functions specified. I have the delta function and the omega function specified. This corresponds to my delta function, and this corresponds to the omega function. Okay, everyone, any questions?
Professor, what's the second column of the output? Like, is that?
Oh, it's just yeah, it's just telling you the English meaning of it.
Oh, all right, makes sense. Thank you.
Yeah, it's just that. Yeah.
How did you get your outputs?
From the state machines, yeah. Right, in GNS state, I want the green light to be north-south green light to be on. So remember, it was one hot coded. So this is the green north-south, and then by our rules of operation, the east-west has to be red.
Oh, so does the output not like account for the fact that there are two different possible, given whether it's car east west is true or false?
Well, it's a Moore machine. So if I'm in GNS state, then output for north-south is green and output for east-west is red. There is no dependence on car east-west.
No, I'm saying like if car east west is there, then wouldn't the GNS turn to YNS?
Right, but that will happen at the state transition, right? When you move to the state YNS, then you will have that output. But if I am in state GNS, then GNS, the meaning of GNS was that north-south is green.
Oh, okay.
Right?
Okay.
How we had decided to state, right? So yes, we will move from GNS to YNS if car east-west is there. But when I am in GNS, the output is this. Only when I move to YNS would the output change, right? So it's a Moore machine. In a Moore machine, outputs are independent of the inputs, right? They depend only on.
All right.
Okay, so let's move on. So now we are still missing one. Before we can finish the design, I need to figure out what bits to use for the states. So I have 4 states. So we need to figure out what to have them in bits. And once we do that, once we replace GNS, YNS, GEW, YEW by some bit vectors, then I would have basically 2 truth tables, and then we can kind of work off that. So the state assignment problem basically is that we have to encode the symbolic state. So thus far, we were giving names to the states. They were symbols, GNS, YNS, GEW, YEW. But now I need to give them bits so that I can design my hardware. So there are 2 common ways of encoding the states: one-hot coding and binary coding. Okay. So in binary coding, we use log2 times the number of states, that many bits, and one-hot coding, we use as many bits as the number of states. So in our example, one-hot coding would mean 4 bits, and binary coding would mean 2 bits. Okay. So 4-bit, 2-bit in our example. So let's see how we do it. So let's say we do one-hot coding. So the idea is that we think of our state vector as having 4 bits, and we assign each state to one of those bits. So in particular, we basically say GNS means the first bit is 1. YNS means the second bit is 1. GEW means the third bit is 1, and YEW means the fourth bit is 1, as shown in this table. Okay, so it's the one-hot coding. So now I have the encoding of the states, and now let's see how we can translate our design into a piece of hardware. So it turns out if you use one hot coding, then getting to hardware is like quite simple, quite straightforward. Okay, so let's see what will happen. So first thing we do is we have uh, four state bits, right? Our state consists of 4 bits. So I will need 4 flip-flops, right? Because I need a state register with 4 bits. So I will need 4 flip-flops. So what you can do is you can say, I have 4 flip-flops, those boxes that I have drawn. And if I am in state GNS, then the flip-flop which I have called GNS will have a value of 1, and all the other 3 flip-flops will have the value 0. If I am in state YNS, then the flip-flop YNS will have 1, and the other 3 will have 0. If I am in state GEW, then GEW will have 1, and the other 3 will have 0. And finally, if I am in state YEW, then the YEW flip-flop will have 1, and the other 3 will have 0. Okay, so there is a 1-to-1 correspondence in case of one-hot coding. Moreover, my outputs control 2 clusters of light. So there is a north-south set of light and the east-west set of lights. Okay, so now let's see how will we do our design. So let's say I'm in the state GNS. So if I'm in the state GNS, I have to take care of 2 things. I need to move to the right state, and I have to have the output correctly. So let's first focus on the transitions. So if I'm in GNS, and if car east-west is 1, then I have to move to YNS. And so which means that if I'm in GNS, then so there is a 1 in GNS, then next clock tick, I want YNS to become 1 and GNS to become 0. I don't need to worry about GEW and YEW. So the way I can achieve this thing is like the following. I can say, if I'm in GNS, so if this is high and car east-west is high, then I make this guy 1, right? So then YNS will become 1. So if GNS is 1 and car east-west is 1, then YNS will become 1. So I make the flip-flop input 1. And I need to make sure that GNS gets the value 0. So this logic will do that. This logic will basically say that if car east-west is high, right? So if car east-west is high, so then this AND gate will become disabled. And meanwhile, YEW is 0, so GNS will become 0. So if GNS was high and car east-west was high, then in the next clock tick, YNS will become high and GNS will become 0, which corresponds to the transition out here. So this the other part we need to make sure is that if car east-west is 0 and we are in GNS, then we stay in GNS. Again, you would see that also. If car east-west is 0, then this will become active, right? And GNS is high, then GNS will remain high. So I argue that this logic, this thing together, so this logic out here and this logic out here together are implementing what we are seeing out here. And kind of almost you can do a translation just looking at it, right? I mean, that I had a 1 in, I started out with 1, 0, 0, 0. And if car east versus 1, then I want to move to 0, 1, 0, 0. And if car east was 0, then I want to stay in. And so I'll let you stare at that circuit, but it indeed is doing that. That if GNS, so we have one hot coding, so at any given point in time, only one flip-flop will be high. So GNS being high is means YNS, YEW, and GEW and YEW are 0. And so car east-west 1 would result in GNS becoming 0 and YNS become 1, and car east-west being 0 and would cause GNS to remain 1. And the other cases are super simple, because if I'm in YNS, I always need to move to GEW, which means that if this guy is 1, YNS, then in the next clock tick, I want GEW to be 1. So that is just directly connected. And 0 will, uh, and 0 will kick in out here. So let's work that example out also. So let's see. Yeah, I'm going to draw it out here. So let's say we were in the state GNS was 0, YNS was 1, GW was 0, YEW was 0. So let's look at these two cases. So firstly, if YNS was 1, then GW will become 1 unconditionally. GW was 0, so next clock tick YEW will remain 0. And what about GNS? Well, car east-west is 1. So since this guy is 1, so we'll have a 0 out here. GNS was 0. So we'll have 0 feeding in. And so GNS will remain 0. And what about this guy? So car east-west is 1, but GNS is 0. So this one will remain 0. That will go to 0. So this is what will happen in next cycle, next clock tick if car east-west is 1. And likewise, you can work it out that if car east-west is 0, again, you will see the same thing. And same way if GW was 1 and if YEW was 1. So the nice thing out here with one-hot coding is that our hardware kind of looks like our state machine, right? For unconditional transitions, it's kind of just straight transitions. And the only time we have to worry about is when there is some self-edge or something. And then coming up with this logic, you usually kind of stare at the problem and you can literally kind of talk about it, talk your way through it. Okay, so very simple transition logic. Now, the part we are still missing is how do we control the output lights? So we still have to worry about that a little bit. So, so north-south lights. North-south is green when GNS is high. North-south is yellow when we are in the YNS state. And north-south is red when we are not in GNS and not in YNS. So that's exactly what is happening out here. GNS feeds to controlling the green light. YNS feeds to control the yellow light. And then the red basically says it's neither, it's not yellow and not green, so therefore red. And likewise, for the east-west symbol, we have a similar thing. That green comes from, so the green light is being controlled by this. So if I'm in GW, green will be on. If I'm in YW, yellow is on. And red is on if I'm in neither one of them. So the output hardware is very easy also. And in this particular case, these two NAND gates, this gate and this, these two NOR gates, really, they correspond to my output logic. And the gates out here, the AND gate and this AND OR kind of structure, they form my next state logic. So, questions. I know there would be a lot of questions. So, well, and the final thing we need is a clock, obviously. Okay, so that's our final hardware. So one-hot coding, that's super simple stuff. This is what I'll do. So since we are over time now, so I'm going to stop. But I want you to read the chapter in the book to make sure to understand. And then try to work out examples. So just remember, it's one-hot coding. So only one flip-flop will have a 1 and the other flip-flop will have 0 by design. And that will correspond to one of these states. So if GNS flip-flop has a 1, then we are in the GNS state. If YNS has a 1, then we are in the YNS state, and so on and so forth. And then try out like what happens in the next clock tick in various cases. But before I hang up, questions.
Just a general question about the quiz.
Mm-hmm.
If the timer went off and like it kicked us off, did it save?
You know, it clearly saved something because there were some students who came and said they never hit the submit button. And then when I looked at their quizzes, I do see answers for them. What I don't know is that if it's doing some auto saving. What I don't know is the frequency with which it does. So, so unfortunately, the only way is so. Like, did you ever hit the submit button?
No.
No. Okay. So send me a private note, and then I will just share with your. I can send back what responses I see for you, and then you can verify. But the thing is, I am seeing some answers for push students who said like you that they never hit the submit button. One thing I would, in response to my Piazza note today, please do read the instructions. Unfortunately, I tried my best with multiple modalities of communicating that bit because the documentation was a little bit ambiguous. Actually, according to documentation, it doesn't do autosave, but clearly it is doing some autosave, but I don't know the frequency with it does.
Okay, thank you.
Anyone else with questions?
Wait, so when you have the stars here, is that just mean unconditional? Like you have to go from YNS to GW or GW to IW?
Yeah, it's unconditional. Yeah. The book is using the notation of star for unconditional. So, but also intuitively, there's only one edge going out of YNS by EW, right? So you can think of it as again.
And you're designing the circuit considering you're only caring about whether there's a car in the east-west direction, right?
What do you mean?
Like you're not considering the other reset signal, right?
I'm not considering what?
The reset signal?
Oh yeah, we are not considering the reset signal here. Yeah, so no reset.
In that case, the state table for this one would be different from what you've shown before, right?
Well, in the state table that I showed out here, it does not have reset also. It's also ignoring reset. So I have not drawn that state table with reset, right? With reset, I have the state diagram, but we never drew the state table. We never drew this this kind of a table. So the only table we have drawn is the one without reset. Okay. Okay. So the TAs will go over state machines on the discussion section. The state machines is probably the hardest part of the course, particularly how to take a problem and map it, go through the steps. So please do make sure to attend because otherwise you'll have a super hard time in the coming assignments. Okay. So I can't emphasize this is, historically we have found this module and the next one is kind of the ones where people have the most challenges with. So please visit the discussion section. Yeah, go ahead.
So for this example, we used one-hot coding for the states. If we used binary, would that cause the circuit to be more complicated? Yeah,
it does, and I'm going to. I think the subsequent slides have it. Yeah, I do have binary coding also, so I'll show that to you. It's more complex. Yeah.
And in general, would that make would binary coding make the circuit more complicated?
Yes, generally it will. But the issue also is that if you have a state machine with hundreds of states, then the cost of flip-flops can begin to dominate, right? So while you may have a simpler combinational logic with one-hot coding, but let's say I tell you that I have 1024 states. Well, now you are talking about having 1024 flip-flops versus 10 flip-flops. Yeah, that matters, right? And state machines with thousands of states are there. They're very commonly encountered. So in realistic designs. So the challenge is that yeah, one hot coding is probably a reasonable strategy without much of a cost hit for modest number of states. Let's say tens of states, maybe. Even there, it might be a little bit of an issue. But when you are looking at state machines with thousands of states, you have to do some coding. Okay, and then the question becomes which binary coding? Which one do I call 001? Like in this case, let's say I was using 2-bit coding. Which one should be state 00? Which one should be state 01, 1011? That can have an impact too. So the tools which do design and all, they actually have algorithms to figure out what is a good state mapping also. There's a lot of research on that topic, and people have developed algorithms for doing it. I mean, I'm talking about research back from like 1990s or so. I mean, now it's kind of a solved problem. So, but it's not something that you can manually do. It's super painful. So which is why kind of we let the tools do. Sometimes what may happen is your problem may require that some state have a particular value. Like it's very common to give start state all zeros in a binary coded case. Okay, so in which, but then the other states you are free to choose whichever way you want. Okay.
Professor?
Yeah.
In the case of the state machine, while we were still considering reset, what exactly would trigger reset to change?
Oh, what exactly would trigger? So usually, well, two things. Firstly, I'm sure you have encountered like your phone hangs or your computer hangs and there is a soft reset button. So the equivalent of that, my traffic controller is not working properly. I go and hit a reset button without powering it on. Okay, so kind of just bring it back to a sane state. So manually, okay. Second one is right after power up. So usually there is some special circuitry. What it does is when your system starts up, your voltage, like when you power up, it takes voltages some time to kind of stabilize and all. And your flip-flops come up in random states, right? Some come up 1, some come up 0, so you don't know where you are. In fact, in our one hot example, it might not even be a valid one hot code, right? It may come up that way. So usually there will be some special circuit which will make sure that the system is in a valid state. And there is a third one. Sometimes these systems are remote, right? I mean, particularly traffic light controller. And so if they hang, you're not going to send a person to manually reset it. So usually they have a circuit called watchdog timer. And what these watchdog timers do is they keep checking, is the system stuck? And if the system is stuck, they reset the hardware automatically. So that's the third one. So these are some examples on where the reset signal may come from.
Okay, thank you.
Manual, watchdog, and right after power up.
Okay, thank you.
Yeah.
Just one last quick question. And if you look at the state diagram you have, there is an AND gate that feeds into the YNS, right? So one of the inputs of the AND gate is obviously the CAR EW, and the other one is the output of the GNS flip-flop. So then why is it the GNS flip-flop? Because if you would want to turn it to YNS if CAR EW is 1 and GNS is 1. Is that how the logic is?
Yeah, I am in GNS state and CAR East-West is 1.
Oh,
right?
GNS. Well, GNS outputting 1 means that you are in the GNS state.
Remember, it's one hot coding, right? So GNS flip-flop being 1 means I am in GNS state, right? So the state of the flip-flops, GNS 1, 0. So the flip-flops can be only in 4 possible states: 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, which correspond to our 4 one hot coded values, right? I mean, which we decided here. So GNS, if GNS flip-flop has a 1 in it, then that means I am in the GNS state. Okay.
Wait, so how does the flip-flop output 1 from the 1-bit, the one hot-coded representation?
Well, the flip-flop is a 1-bit thing. So my state is split, is my state together is the value of these 4 bits. So like if GNS...
okay. I see what you're saying. So like if you're in the GNS flip-flop is going to be 1 and the remaining 2 are going to be 0. And that's how it's one hot-coded.
So my state vector, my state register is made up of these 4 flip-flops, right?
Huh?
So GN is, and that constitutes the state vector.
And then similarly, if the my other one was, the question was on the YEW wire going into the OR gate. So you're saying that if the YEW is 1, then you want it to go to GNS automatically.
GNS automatically, exactly.
And that's why you have an OR gate. Because as long as one input is 1, it'll just go through as 1.
Exactly.
Oh, okay.
Yeah.
That clarifies things. All right.
Okay. Any more questions? Anyone? Okay, terrific. So see you guys on Tuesday. But meanwhile, please do go to the discussion section tomorrow because I think this topic is not easy. That's why. Okay, bye.
Thank you.
Yeah, thanks.